Welcome to Sleepy Stories. In this episode, we will take a clear and steady look at how the universe manages to stay in motion, even though the night sky appears perfectly calm. The purpose of this story is to help you learn while resting. If sleep does not come right away, that is completely fine. You can relax, follow the gentle explanations, and allow your mind to drift without pressure. If you enjoy relaxing stories that help you learn while winding down, feel free to like this video and subscribe to our channel so you can find more episodes whenever you need them. Simply listen, let your breathing slow, and allow the information to settle at its own pace as we begin exploring the quiet motions that shape the cosmos. When people step outside at night and look up at the sky, the scene often appears perfectly still. The stars hold their positions with remarkable consistency, the darkness stretches in every direction, and nothing seems to move except the occasional passage of a satellite or an airplane. This impression of stillness is natural because the human senses evolved to notice quick changes, not motions that unfold slowly or across vast distances. Even the stars that appear closest to Earth are so far away that their movement is too subtle to detect without precise measurements taken over long intervals. The sky gives the impression of a fixed dome because its motions exist far beyond the scale of daily experience. Yet the stillness is not real. Every point of light in the sky is moving. Many of the stars visible on a clear night travel at hundreds of kilometers per second through the Milky Way. Their change in position is genuine, but the shift is tiny compared to the distances involved. Over a human lifetime, the movement is too slight to notice. Over many thousands of years, constellations gradually change shape. The slow pace of these changes helps explain why stillness can feel so convincing. What looks unmoving is simply moving at a rate that lies outside human perception. Earth itself is part of this motion. The planet orbits the Sun, and the Sun orbits the center of the Milky Way. Our entire solar system drifts through interstellar space, influenced by the gravitational pull of surrounding stars and the overall structure of the galaxy. Because we move with these systems, we do not feel the motion directly. It is similar to riding in a smooth train. When the motion is steady, the sense of movement fades into the background, and stability becomes the dominant impression. Shared motion creates a sense of calm, even when speed is significant. This idea of shared motion can be extended to the galaxy itself. The Milky Way contains hundreds of billions of stars, all following paths shaped by gravity. Most of these paths look like broad circles or gentle ellipses around the galactic center. Although individual stars move at great speed, their collective motion appears quiet and orderly because it remains consistent over long periods. The galaxy rotates so slowly in human terms that even noticeable changes in its structure require millions of years to detect. This gradual pace contributes to the sense that the cosmos rests in perfect balance, even while everything within it is in continuous motion. The universe also expands, increasing the distance between galaxy clusters over immense timescales. This expansion influences motion on the largest scales, creating patterns that appear fixed only when viewed from the perspective of a short human life. Expansion does not create sudden shifts or turbulence. Instead, it gently stretches space. The effect is so gradual that it feels invisible, yet it plays a major role in shaping the long-term arrangement of matter. This helps explain why the night sky can look so stable while remaining part of an ever-changing universe. At the smallest scales, motion is equally present. Atoms and molecules are never truly still. Their particles vibrate, rotate, and interact continuously. Even in extremely cold environments, where the motion slows to a minimum, it never stops entirely. This microscopic activity forms the basis of temperature and supports chemical processes that influence everything from the behavior of interstellar gas to the interior of planets. When viewed this way, motion becomes a universal property, extending from the tiniest structures to the most distant galaxies. Human perception creates the illusion that stillness is common, yet physical reality reveals the opposite. The appearance of calm arises from the scale of the universe, the slowness of many cosmic processes, and the shared motions that shape our experience. Stillness becomes not a physical state, but a product of limited senses. By understanding this, the night sky begins to look different. The calmness remains, but the illusion of stillness fades. In its place emerges an appreciation for the quiet motions that maintain the structure of the universe. The opening of this story sets the foundation for a deeper exploration of how motion defines the cosmos. Every part of the universe participates in it. Every structure depends on it. And even when motion cannot be seen, it continues silently, supporting the patterns that make the universe coherent and balanced. With this perspective, the apparent stillness of the night becomes a reminder of the vast and gentle motions that shape the cosmos. Motion is one of the most fundamental conditions of the universe. It does not appear occasionally or under special circumstances. It is woven into the behavior of matter and energy everywhere. The sense that motion is rare arises from human experience, where stillness is familiar and motion seems like an interruption. In physical terms, however, stillness is usually an illusion created by shared movement or by motion too slow or subtle to detect. This makes motion a universal backdrop rather than a temporary state. When an object appears motionless, it is often because it shares the same motion as its surroundings. A person standing in a moving train does not feel the train's velocity because everything nearby moves together in the same direction and at the same speed. In a similar way, Earth moves through space with the Sun, and the Sun moves with the Milky Way. The entire solar system participates in a larger flow. Because all nearby objects share this long journey, the sense of motion fades. Stability emerges from the absence of differences rather than the absence of movement. Even when motion is not shared, it may be too slow for human senses to register. A distant star, shifting slightly across the sky over many decades, will not appear to move at all. Mountains, continents, and oceans participate in geological motion that unfolds across millions of years. The scale of these processes extends beyond direct perception, creating an impression of stillness that masks continuous activity. By understanding this, it becomes clear that the appearance of rest is often a matter of perspective. Motion also takes many different forms. It can be linear, circular, oscillating, rotational, or irregular. It can be driven by gravity, pressure, electromagnetic interactions, or thermal energy. Some motions repeat in cycles, such as the rotation of planets or the vibration of atoms. Other motions drift gradually, such as interstellar gas clouds or galaxy clusters. Although these processes differ from one another, they share a common feature. None of them require constant intervention to continue. In empty space, motion persists naturally because nothing slows it down. This persistence arises from another fundamental principle. In the absence of opposing forces, a moving object remains in motion. Space is so empty that objects can travel across vast distances without encountering significant resistance. A planet orbiting a star will maintain its path unless acted upon by other influences. A spacecraft that leaves the solar system will drift indefinitely unless it interacts with another gravitational field. This natural longevity of motion explains why the universe remains dynamic without constant renewal. Energy offers an additional perspective. Motion is a form of energy, and energy does not disappear. It changes form. When motion slows in one place, energy often reappears elsewhere as heat, radiation, or structural change. Gas clouds collapsing under gravity convert potential energy into heat. Rotating systems adjust their patterns but preserve total angular energy. These transformations maintain continuity across different scales. Nothing reaches perfect rest because energy always finds a new expression. What emerges from this view is a universe where motion is the rule rather than the exception. Objects do not need to be forced into movement. They need forces to stop moving. The cosmos is not a silent arrangement of fixed structures but a continuous interplay of drifting, rotating, stretching, and evolving systems. This motion does not disturb the quiet appearance of the night sky. Instead, it supports it. The sky looks stable because the motions within it are balanced, long-lasting, and arranged over scales far larger than the human mind naturally grasps. By recognizing motion as a natural condition that fills every part of the universe, the calm view of the sky takes on a new meaning. Stillness becomes a perception shaped by limits, while motion becomes the true state of nature. With this understanding, the idea of a restless universe gives way to something more accurate. The cosmos moves not with urgency, but with steady continuity. Its quietness is a reflection of scale, patience, and balance, rather than a sign of inactivity. The origins of cosmic motion reach back to the earliest moments of the universe. To understand why everything moves, it helps to consider how space itself began to change. In the first fractions of a second after the universe came into existence, space expanded. This expansion did not push matter outward into an empty void. Instead, it increased the distance between all points in space at once. The result was a smooth and uniform growth that set the foundation for the motions that continue today. Expansion was not a burst that faded. It became part of the fabric of the universe. As space expanded, tiny irregularities in density began to grow. Regions with slightly more matter attracted even more through gravity. Over long periods, these regions developed into clusters of galaxies. The expansion did not stop this process. Rather, it provided the backdrop against which matter gathered and structures formed. Gravity pulled matter inward, while expansion stretched the space between distant regions. These two effects worked together, shaping the universe without removing motion. Instead of settling into a static state, matter remained in constant movement, responding to the interplay of gravity and expansion. One important idea is that motion did not need to be added to the universe after expansion began. The expansion itself created conditions in which motion was unavoidable. As the space between regions increased, matter followed the shifting geometry. Even if a galaxy had no internal speed of its own, it would still drift apart from others because the space joining them continued to stretch. This gradual drift does not feel like movement when viewed from inside a galaxy, yet it is part of a large-scale pattern that influences the long-term behavior of the cosmos. The early universe also contained energy in forms that contributed to motion. Radiation carried momentum. Particles interacted through collisions, exchanging energy and direction. Over time, these interactions shaped the distribution of matter. As the universe cooled, particles combined to form atoms. These atoms moved through space, sometimes gathering into clouds that later developed into stars. The motions at this stage were gentle but persistent, guided by temperature differences, pressure gradients, and gravitational attraction. Even during this early phase, nothing came to rest. The formation of galaxies illustrates how expansion and gravity combined to create orderly motion from initial irregularities. As matter collected into large structures, it began to rotate. Rotation was not imposed from outside. It emerged naturally from the uneven distribution of matter and the conservation of angular momentum. When a region of gas contracted under its own gravity, any slight initial rotation became stronger. This rotation helped shape the flattened disks of early galaxies. The motion did not disrupt formation, it supported it, guiding matter into patterns that persisted. Today, observations of distant galaxies reveal that expansion continues. Galaxies are not moving through space in a conventional sense. The space between them stretches, carrying them along. This provides insight into the scale of cosmic motion. It does not require a specific direction or external cause. It arises from the nature of space itself. The galaxies maintain their own internal motions through gravity, while drift on larger scales follows the expansion. The combination creates a universe in which motion operates simultaneously on different levels without conflict. Understanding these early processes shows why motion is so deeply embedded in the universe. From the beginning, cosmic conditions favored activity over stillness. Expansion shaped the large-scale structure. Gravity shaped the local structure. Energy transformations guided smaller-scale behavior. No part of the universe formed without movement, and no part has remained still. The motions observed today are the continuation of patterns set long ago, influenced by the same principles that shaped the first structures. The calm appearance of the night sky can feel far removed from the dynamic events of the early universe. Yet the two are connected. The quiet patterns visible now reflect processes that began in the earliest moments. The universe has kept moving because nothing in its physical laws promotes rest. Motion is not an addition to the cosmos. It is a continuation of its origins, expressed in the persistent expansion of space and the long-lasting influence of gravity. Many ideas about cosmic motion become clearer once the nature of expansion is distinguished from the idea of an explosion. An explosion sends material outward from a central point into surrounding space. It creates shockwaves, debris, turbulence, and a clear direction of travel. None of these features describe the behavior of the universe. Cosmic expansion does not involve fragments of matter rushing away from a center. Instead, it involves space itself increasing in scale. Every region participates equally in this expansion, and this makes the motion uniform rather than chaotic. Understanding this difference allows the patterns seen across the universe to be interpreted with far greater clarity. The absence of a central origin helps explain many observations. When astronomers measure the light from distant galaxies, they find that most of them recede from Earth. This does not mean all galaxies are fleeing from a privileged position. Any observer in any galaxy would see a similar pattern. This uniformity follows naturally from expansion. When space grows, distances stretch everywhere at once. A person inflating a balloon covered with small dotted markings will see every mark move away from every other mark. None of the marks act as a center. The universe behaves in a similar way. The expansion does not push galaxies outward. It increases the space between them. This growth of space is gentle rather than violent. It does not generate wind or pressure in the usual sense. Galaxies do not feel a force pushing them. They simply follow the geometry of the expanding space they occupy. This is why the expansion can continue without disturbing the internal structure of galaxies or clusters. Gravity remains strong enough locally to bind stars, planets, and entire systems together. Expansion is only noticeable across much larger scales, where gravity grows too weak to prevent the gradual stretching of distances. This distinction helps explain why the universe looks so orderly. If the early universe had exploded in the familiar sense, matter would have dispersed unevenly. Some regions would have been blasted apart, while others would have collapsed. Turbulent patterns would dominate. Instead, expansion created a backdrop of smooth growth. Gravity then acted on small irregularities to form galaxies and clusters. These processes operated together rather than in opposition. Expansion set the large-scale arrangement, while gravity shaped the local structure. The cooperation between these influences produced a universe that is both dynamic and stable. Another important point is that expansion does not require a medium. Sound travels through air, and ripples travel through water, but the expansion of the universe does not travel through anything. Space itself grows. This feature helps explain why expansion does not create noise or shock. It alters the distances between objects without sending a wavefront that sweeps across space. The growth is smooth, steady, and continuous. The rate of this growth can change over time, but the process remains gentle on the scales where galaxies form and evolve. When thinking about motion, it is also helpful to consider how expansion creates the appearance of recession without requiring galaxies to move through space at high speeds. A distant galaxy may seem to move away rapidly, yet its internal behavior remains unchanged. Stars continue to orbit their centers, gas continues to circulate. The galaxy's own motion is shaped by gravity, not by expansion. The sense of recession comes from the stretching of space between observers and distant structures. This perspective explains why galaxies with significant recession speeds remain intact. Their internal motions are unaffected because expansion does not pull them apart. The quiet behavior of expansion also means that motion on smaller scales can proceed undisturbed. Stars form from collapsing clouds, planets orbit their stars, clusters of galaxies remain gravitationally bound. Expansion does not disrupt these processes any more than a slowly inflating balloon disrupts the arrangement on its surface. The two scales coexist. The universe grows on the largest scales while maintaining complexity on intermediate and small scales. By separating expansion from explosion, a more accurate picture of the universe emerges. The calmness of the night sky no longer seems surprising. The expansion of space is a slow, continuous process that supports long-term stability. It influences the motion of galaxies without disturbing their internal structure. It provides the backdrop for the formation of stars, the evolution of galaxies, and the persistence of cosmic patterns. When viewed this way, expansion becomes an essential part of the quiet rhythm governing the universe. Galaxies provide one of the clearest examples of how different forms of motion coexist in the universe without conflict. They do not glide independently through an empty backdrop. Instead, they occupy regions of space that gradually stretch as the universe expands. This means a galaxy does not need to travel outward to create growing distances between itself and others. The space it inhabits slowly increases, carrying it along. At the same time, gravity binds the matter inside the galaxy, ensuring that stars, gas, and dust remain part of a coherent structure. These layers of motion operate together, creating patterns that are stable even as the universe changes. Inside a galaxy, gravity dominates. Stars follow paths shaped by the distribution of mass within the galactic disk and halo. Their motions form large-scale spirals or more irregular arrangements depending on the galaxy's history. This behavior does not conflict with the expansion of space. Expansion is simply too weak on these scales to alter the structure. A galaxy remains internally intact because the gravitational attraction between its components far outweighs the stretching effect of the expanding universe. This balance allows galaxies to act as islands of complexity in a cosmos shaped by gentle, large-scale motion. Beyond a galaxy's boundaries, the influence of gravity gradually decreases. Between clusters of galaxies, expansion becomes more noticeable. These vast regions contain relatively little matter, so nothing counteracts the slow stretching. As a result, clusters grow more distant from one another over long intervals of time. Yet within each cluster, galaxies continue to orbit their shared center of mass. The combination of local gravitational binding and large-scale separation creates a layered pattern where different types of motion maintain harmony rather than tension. This layered behavior explains why the universe can appear calm, even though it contains many overlapping processes. One helpful way to picture this is to imagine a collection of small, dense objects floating in a medium that slowly expands. The objects remain bound to each other within small groups, but the distance between groups increases gradually. The objects themselves retain their internal structure, while the environment around them grows. Although this image simplifies the physics, it captures the idea that galaxies participate in multiple motions at once. Their internal dynamics follow the familiar behavior of gravity, whereas their long-range positions shift because the space between them grows. Observations of distant galaxies confirm these patterns. The light they emit shows that most galaxies are receding from one another. The farther away a galaxy is, the faster it appears to recede. This relationship supports the conclusion that expansion governs the large-scale motion of the universe. Yet these same galaxies display internal motions that remain entirely unaffected by their recession speeds. They rotate, form new stars, evolve through collisions, and carry histories shaped by billions of years of gravitational interaction. The recession is a property of space, not of the galaxies themselves. The coexistence of local stability and large-scale motion reveals why the universe does not settle into stillness. Gravity shapes the behavior of stars, planets, and clusters, creating structures that endure across immense spans of time. Expansion shapes the behavior of these structures relative to one another, creating the long-term drift that defines the growth of the cosmos. Neither influence cancels the other. Instead, they carve out different domains in which motion takes its characteristic form. By understanding this, the calm appearance of galaxies becomes easier to interpret. Their quiet arrangement in the night sky reflects the presence of two governing patterns. One pattern maintains coherence, while the other guides separation. The result is motion that is steady, predictable, and layered across different scales. This combination gives the universe its sense of order, making the night sky seem serene while revealing a deeper rhythm of movement that spans both local and cosmic distances. When the universe is viewed across its largest scales, new patterns of motion become visible. Galaxies do not distribute themselves randomly. Instead, they form an intricate arrangement known as the cosmic web. This structure consists of long filaments containing clusters of galaxies, surrounding vast regions of relatively empty space called voids. Although this pattern has remained recognizable for billions of years, it is not static. The filaments stretch, the voids expand, and clusters shift slowly through the web. The pace of these changes is gentle, occurring across timescales far beyond direct human observation. Yet these slow motions help shape the overall character of the universe. Gravity plays an essential role in forming and maintaining this large-scale pattern. Regions that began with slightly more matter developed into filaments and clusters as gravity pulled additional material toward them. Less dense regions evolved into the vast voids that dominate much of the universe. As space continues to expand, the voids grow larger, allowing the filaments to lengthen and stretch. Motion at this scale is subtle because distances are immense and the forces involved are distributed over great volumes. Even so, the pattern continues to evolve, revealing the quiet influence of expansion and gravity acting together. The slow drift of entire clusters within this web offers another example of motion unfolding in a calm and orderly way. A cluster can move through the surrounding space due to gravitational attraction from nearby structures or the uneven distribution of mass across the web. These movements are extremely gradual. Over a human lifetime, the position of a cluster relative to the larger web hardly changes. Over hundreds of millions of years, however, the shift becomes significant. This long-term evolution helps maintain the dynamic nature of the cosmic web while preserving its overall shape. Observations made with large telescopes and cosmic surveys provide evidence of these vast motions. Maps of the distribution of galaxies reveal filaments that extend across hundreds of millions of light-years. They also show the expansion of voids and the flow of galaxies along filamentary paths. These patterns demonstrate that motion does not stop at any particular scale. Instead, it becomes part of larger frameworks that extend far beyond the range of individual galaxies. The gentle pace of these changes reflects the enormous distances involved. Even small velocities produce only modest shifts across cosmic expanses, yet those shifts accumulate steadily over long periods. The idea that the universe evolves slowly on large scales offers a helpful perspective for interpreting the night sky. The arrangement visible today is not permanent. It is a moment within a continuous process that reshapes the distribution of galaxies over time. This does not disrupt stability, it enhances it. Because the changes occur gradually, structures have time to adjust and develop without experiencing sudden disturbances. This contributes to the impression of calm that characterizes the universe. Motion does not undermine order, it supports it. Another important feature of the cosmic web is that it reveals how interconnected the universe remains despite the vast distances involved. The positions of galaxies and clusters are not isolated. They respond to the combined influence of gravity across enormous regions. Even small variations in mass distribution contribute to the slow drift of large-scale structures. Expansion provides the overall stretching, but gravity adds direction and subtle shaping. Together, these influences produce a universe where motion and stability coexist naturally. By considering these long-term patterns, it becomes clear that stillness is not part of the universe's design. Even when motion is too slow to observe directly, it leaves traces in the arrangement of galaxies and the growth of the cosmic web. These gentle shifts tell a story of steady change. They reveal a cosmos where stability arises from ongoing motion rather than from rest. When viewed across the largest scales, the universe appears calm because its motions unfold in measured, predictable ways, guided by the balance between gravity and expansion. Gravity shapes much of the motion observed in the universe, not by stopping movement, but by guiding it. It does not bring objects to rest. Instead, it organizes their paths, allowing motion to become stable and predictable. This quality makes gravity different from the forces commonly encountered in daily life, such as friction or air resistance, which tend to slow things down. In the emptiness of space, gravity acts without these opposing influences. It curves trajectories, pulls matter together, and sets the conditions in which long-lasting structures can form. Because of this, gravity becomes one of the main reasons motion remains orderly across the cosmos. When gravity acts on scattered material, it encourages matter to collect into shapes that reveal its influence. A drifting cloud of gas will not remain dispersed forever. Over time, gravity will draw it inward, causing it to shrink and compress. This gathering does not remove motion, it redirects it. As the cloud contracts, any slight rotation it possessed becomes more pronounced. Particles spiral inward, adjusting their paths as they fall toward regions of higher density. What begins as a disordered collection of drifting atoms becomes an organized system with a clear structure. Rotation emerges naturally from this process, demonstrating how gravity transforms random motion into stable patterns. The orbits seen throughout the universe provide a clear example of gravity's organizing role. When an object moves near a massive body, gravity bends its path. If the object has enough sideways motion, it enters an orbit rather than falling straight inward. This orbit is not a static state, it is continuous motion shaped by gravity's pull. The object falls toward the massive body, but its sideways motion causes it to miss, creating a stable loop. This balance can persist for millions or billions of years. Nothing in the orbit remains still. The enduring pattern arises from gravity's ability to guide motion rather than halt it. Clusters of galaxies show this principle at even larger scales. Although individual galaxies drift apart due to the expansion of space, clusters remain bound by gravity. The galaxies within them move in complex paths around the cluster's center of mass. Some follow broad arcs, while others take more irregular routes shaped by interactions with neighboring galaxies. These motions do not collapse the cluster or tear it apart. Instead, they maintain its structure. Gravity supplies the coherence, ensuring that the galaxies remain part of the same large-scale system even as space expands on larger distances. The quiet behavior of gravity is part of what makes the universe feel so orderly. Its influence spreads across vast regions without overwhelming them. It does not push or collide, it simply shapes the possible paths that matter can take. Even small variations in mass distribution create subtle differences in gravitational pull, guiding the slow drift of galaxies and affecting the long-term evolution of cosmic structures. These shifts are gentle, accumulating over enormous periods of time. The result is motion that remains smooth rather than chaotic, reflecting gravity's steady influence. Another aspect of gravity's role in cosmic motion is the way it balances energy in large systems. When a cloud collapses or a group of stars forms, gravitational energy is converted into heat and motion. This conversion maintains activity within the system. Stars rotate, gas circulates, magnetized regions shift and twist. Gravity supplies the framework that keeps these processes stable. Even when stars age and change, their internal and external motions continue to respond to gravity's pull, preserving order during transitions. By understanding gravity as an organizer rather than an opposing force, the behavior of the universe becomes easier to interpret. Motion does not work against gravity, it works within the paths gravity defines. This partnership explains why cosmic structures endure and why their motions remain calm and predictable. What appears serene in the night sky reflects gravity's quiet guidance. Motion persists because gravity provides the stability that allows it to continue without interruption. Orbits reveal one of the most elegant expressions of motion shaped by gravity. They appear simple when drawn on a diagram, yet the behavior behind them is subtle and precise. An orbit forms when an object has enough sideways motion to avoid falling directly into a massive body, yet not enough speed to escape its gravity entirely. The result is continuous falling that never reaches the surface. The object is always drawn inward, but it moves forward quickly enough that the surface curves away beneath it. This balanced state allows motion to persist without requiring additional energy. It is a natural outcome of gravity acting on a moving body in a region of empty space. Understanding orbits helps explain why planets follow stable paths around stars and why stars trace long arcs around the centers of galaxies. Nothing pushes them along these routes. Their motion continues because nothing removes it. In the vacuum of space, there is no air resistance and no friction to slow them down. Gravity supplies a constant inward pull, while momentum carries them forward. These two influences remain in balance unless an outside force alters the system. This stability allows orbits to last for millions or even billions of years, creating a predictable rhythm that structures planetary systems and galaxies alike. The variety of orbital shapes demonstrates how flexible this balance can be. Some orbits are nearly circular, with only small variations in distance from the central body. Others are elongated, drawing objects far from the center before pulling them back again. Comets often follow such stretched paths, spending long periods in the cold outer regions before returning briefly to the inner system. The shape of an orbit depends on the object's speed and its distance from the central mass at the moment the orbit forms. Despite these differences, the underlying principle remains the same. The orbit is a continuous motion maintained by gravity. Orbits can also interact with one another in quiet ways. When two bodies move near each other, they may exchange energy, altering the size or shape of their paths without disrupting the overall stability of the system. Planetary systems frequently contain resonances, where the orbital periods of different planets form simple numerical ratios. These resonances do not cause chaos. Instead, they enhance stability by repeating gravitational influences in a regular pattern. The listener can imagine a series of linked motions, each one reinforcing the others through predictable timing. This is another way that motion becomes an organizing principle rather than a source of disorder. The stability of orbits does not mean they are permanent in every circumstance. Over long periods, gravitational interactions, tidal effects, or the gradual loss of energy through radiation can alter them. Stars in dense regions may shift their paths due to encounters with neighboring stars. Planets may migrate within their systems if gravitational forces redistribute momentum. Even so, these changes unfold slowly. The predictability of orbits remains intact across immense timescales, demonstrating the quiet resilience of motion shaped by gravity. The concept of orbital motion also helps explain how systems form in the first place. When a cloud of gas collapses under gravity, slight differences in motion cause the material to flatten into a rotating disk. Particles within the disk follow curved paths, gradually accumulating into planets, moons, and debris. The rotation of the original cloud is not lost. It becomes part of the architecture of the planetary system. The resulting orbits reflect the history of that early motion, preserved through the conservation of angular momentum. Even beyond planetary systems, orbital behavior shapes the structure of galaxies. Stars orbit the galactic center, and their paths create the spiral or elliptical patterns seen in different types of galaxies. These orbits do not interfere with one another because the distances between stars are enormous compared to their sizes. Each star follows its own course, guided by the combined gravitational pull of the galaxy. This produces a smooth, coherent rotation rather than collisions or abrupt changes. The scale of the system allows motion to unfold in quiet, ordered ways. When viewed through the lens of orbital dynamics, the universe appears to favor motion that sustains itself. Orbits provide long-lasting patterns that remain stable despite the complexity of the systems involved. They show how gravity and momentum can work together to guide motion into predictable forms. The calm appearance of the sky is rooted in these enduring motions. The stars and planets follow paths shaped by principles that maintain order even as everything continues to move. Falling is one of the simplest motions to observe on Earth, yet in the universe it takes on a broader and more continuous meaning. On our planet, falling usually ends when an object reaches the ground. In space, where there is no surface to interrupt the motion, falling can continue indefinitely. When an object moves under the influence of gravity alone, without encountering resistance or a solid boundary, it follows a curved path determined by the distribution of mass around it. This extended form of falling becomes the foundation for many cosmic motions, from the trajectories of comets to the long arcs traced by stars around galactic centers. A key idea is that falling does not always mean moving straight inward. When an object has sideways motion, gravity pulls it into a curved path rather than a direct plunge. If the forward motion is strong enough to keep the object from reaching the center, the result is a stable orbit. In this sense, an orbit is continuous falling. The object is always being drawn inward, yet never arrives. It is caught in a balance between gravity and momentum. This understanding reveals why orbital motion is not separate from falling but an extension of the same behavior under different conditions. Falling on cosmic scales can also involve interactions far more complex than a simple curved path around a single body. In a cluster of galaxies, for example, many gravitational influences act at once. A galaxy may fall toward the combined mass of the cluster while also responding to smaller variations within that environment. The resulting path is neither circular nor predictable in a simple way, yet the motion remains smooth. There is no sudden change in direction or violent turbulence. Instead, the galaxy follows a long and gentle drift shaped by the overall gravitational field. This quiet behavior illustrates how falling provides structure even in large and varied environments. Another example of extended falling occurs when galaxies approach each other. Their mutual attraction draws them closer over millions of years. They do not collide immediately. Instead, they follow elongated paths, shaped by their speeds and mass distributions. The interaction may eventually lead to a merger, creating a new, larger galaxy. Even in these dramatic events, the motion is governed by the same principles. Gravity pulls the systems together, while momentum determines how they move as they approach. The process unfolds gradually, showing that falling remains a powerful yet calm form of motion even on such large scales. Stars within galaxies also participate in continuous falling. Each star moves under the influence of the galaxy's total mass. It is always being drawn inward, yet its forward motion prevents it from collapsing into the center. This creates a pattern where stars follow long arcs around the galactic core. Many of these paths overlap without leading to collisions because the distances between stars are vast compared to their sizes. Each star experiences a smooth gravitational pull that maintains its course. The result is a galaxy shaped by billions of individual motions, all of them forms of falling extended over immense periods. Falling also influences the behavior of interstellar material. Clouds of gas drift through space under the combined effects of gravity from nearby stars, past interactions, and the distribution of mass within the galaxy. These clouds slowly change shape and direction as they fall toward regions of higher density. Over time, falling can lead to the formation of new stars, planets, and other structures. The energy gained during the fall contributes to heating the cloud, eventually allowing fusion to begin. Falling does not represent an end to motion. It sets the stage for new forms of activity. By expanding the definition of falling to include long-lasting, curved, and stable paths, a clearer picture of the universe emerges. Motion does not require constant input of energy. It continues because nothing interrupts it. Falling becomes a central mechanism through which gravity shapes the cosmos. Instead of being a brief event with a single outcome, it becomes a long and continuous process. The calm behavior of objects in space reflects this extended falling. They move in ways that appear quiet and steady because gravity guides their paths without rushing them. When viewed at the scale of galaxies, clusters, and interstellar clouds, falling becomes one of the most enduring motions in the universe. Angular momentum provides another reason why motion persists throughout the universe. It describes the tendency of rotating systems to maintain their spin unless acted upon by an external influence. This principle applies to objects of every size, from atoms to stars to galaxies. Once a system begins to rotate, that rotation becomes part of its behavior. Without friction or other forces to remove it, the motion endures. Angular momentum is conserved, meaning it does not vanish or weaken on its own. Because of this, rotation becomes one of the most reliable and lasting forms of cosmic motion. The formation of rotating systems often begins with slight imbalances. A cloud of gas drifting in space rarely has perfectly uniform motion. Small variations in the way particles move create a gentle, uneven rotation. As gravity pulls the cloud inward, this rotation increases. The particles fall toward the center, but because they are not moving in perfectly straight lines, they begin to orbit one another. The collapsing cloud flattens into a disk, and the material moves more quickly around the center as the cloud contracts. This behavior follows naturally from the conservation of angular momentum. The faster rotation is not added by an external force. It emerges from the geometry of the motion as the cloud shrinks. The same principle explains why planets orbit the stars that form at the center of these disks. Dust grains and gas particles within the disk collide and accumulate, eventually growing into planetesimals and then planets. Each of these bodies inherits the rotational motion of the disk. Their orbits reflect the history of the original cloud and the way it responded to gravity. Even after planets form, the angular momentum they hold continues to support their motion. They travel along stable paths because nothing removes the energy associated with their rotation around the star. Stars themselves rotate for similar reasons. The gas that collapses to form a star carries its own angular momentum. As the material draws inward, rotation increases. The young star spins rapidly before slowing slightly through interactions with magnetic fields and stellar winds. Even so, rotation persists throughout the star's life. This spin influences the distribution of temperature, the behavior of magnetic fields, and the flow of material in the star's interior. Angular momentum provides a framework that shapes the star's development while maintaining the motion that began long before the star ignited. Galaxies show the same pattern at a much larger scale. The Milky Way rotates because the gas and stars that formed it inherited angular momentum from earlier motions in the universe. Over time, the galaxy evolved into a structure where billions of stars orbit the center. Each of these stars contributes to the overall rotation. The galaxy's shape, whether spiral or elliptical, reflects how angular momentum guided its formation. Despite the complexity of interactions within a galaxy, the conservation of angular momentum ensures that the rotation continues. No process removes it entirely, so the motion persists for billions of years. Angular momentum also influences interactions between cosmic systems. When two galaxies approach each other, tidal forces can redistribute angular momentum between them. This exchange alters their shapes and internal motions, without eliminating the rotation that either galaxy carries. During mergers, angular momentum plays a role in forming new structures, such as elongated streams of stars or rotating cores. Even in these complex scenarios, motion remains a defining feature. The conservation principle continues to guide behavior even when systems interact in intricate ways. The persistence of rotation across the universe highlights how deeply motion is embedded in the behavior of matter. It shows that the universe does not favor rest. Instead, it maintains movement through laws that preserve energy and momentum. Angular momentum acts as a kind of memory, carrying the history of motion across time. Every rotating cloud, spinning star, and orbiting planet reflects earlier stages of the universe. The calmness of these motions arises from their stability. Nothing disrupts them, so they continue without hurry. By understanding angular momentum, the quiet motion seen throughout the cosmos becomes easier to appreciate. Rotation is not fleeting, it is an enduring part of the physical world. It survives the formation of stars, the growth of galaxies, and the interactions between distant systems. The universe stays in motion because the principles governing it ensure that once movement begins, it continues. The patterns shaped by angular momentum become long-lasting features, contributing to the steady and balanced behavior observed in the night sky. The formation of a star begins long before any light appears. It starts within a cold, drifting cloud of gas and dust that moves through a region of space under the influence of gravity and past interactions. These clouds span many light years and contain material that has accumulated from earlier generations of stars. They are never motionless. Turbulent currents, temperature differences, and external forces gradually shape their behavior. Over long spans of time, slight variations in density grow. A region with even a small excess of mass will draw in more material, becoming denser. As gravity strengthens, the inward pull becomes more pronounced. The cloud does not collapse suddenly. It contracts slowly, responding to the balance between gravity and internal pressure. As the cloud contracts, its motion becomes more organized. Material falls inward, but because it does not move in perfectly straight lines, the collapsing region begins to rotate. This rotation increases as the cloud becomes smaller, following the conservation of angular momentum. The structure flattens into a disk, with most of the mass gathering at the center. The motion of the material within the disk is calm and steady. Gas spirals inward, heating as it falls and compresses. The growing warmth comes from the conversion of gravitational energy into heat. This increase in temperature marks the beginning of a long transformation that will eventually lead to the birth of a star. At the center of the disk, Where density is highest, matter becomes tightly compressed. The inward fall of gas raises the temperature until the core reaches the point where hydrogen nuclei begin to fuse into helium. This process releases energy, creating outward pressure. When the inward pull of gravity and the outward pressure of fusion reach equilibrium, the object becomes a stable star. Even at this stage, motion remains essential. Particles in the core move rapidly, carrying energy outward. Layers of gas circulate as heat rises and cooler material sinks. The surface shifts through convection, rotation, and magnetic activity. A star shines because its internal motions continue without pause. The surrounding disk does not disappear when the star ignites. It remains as a rotating structure of gas and dust. Over time, particles collide and stick together, gradually growing into larger bodies. Some become planets. Others remain as asteroids or comets. These objects inherit the motion of the disk that created them. Their paths reflect the history of the cloud from which the star was born. The formation of a planetary system is another stage in the continuous motion that began long before the star existed. Even after a star reaches maturity, its internal and external motions remain essential to its behavior. Within the core, fusion continues as a constant interplay between heat and pressure. Energy moves outward through layers of radiative transfer and convection. The surface shifts in patterns influenced by rotation and magnetic fields. Over time, the star may lose material through stellar winds, shaping the environment around it. These processes occur steadily, guided by well-understood physical principles. Motion does not disrupt the star, it sustains it. Surrounding the star, planets, dust, and gas continue to move in predictable paths. The star's gravity provides the structure that keeps these motions stable. The planetary system becomes a long-lasting arrangement where rotation, orbit, and internal processes maintain a steady balance. Even interactions with passing stars or distant clouds do not remove the overall order. They merely adjust the details of the existing motions. By examining the formation and behavior of stars, it becomes clear that motion plays a central role at every stage. A star is not an object that emerges from stillness. It is the result of motion guided by gravity, shaped by angular momentum, and sustained by energy flowing through its core. What appears from a distance as a point of steady light is in fact a complex system where continuous motion supports stability. The calm appearance of a star reflects the balance of these internal and external motions rather than the absence of activity. Stars appear as steady points of light in the night sky, yet each one travels through the Milky Way on a long and gentle path shaped by gravity. Their motions are not chaotic. They follow predictable routes, determined by the distribution of mass within the galaxy. Every star feels the combined pull of billions of others, creating a gravitational field that guides their movement around the galactic center. This path is often an elongated curve rather than a perfect circle. Even so, the star remains bound to the galaxy, continuing its journey across vast distances in a motion that is smooth and continuous. The speeds involved can be astonishing by everyday standards. Some stars move at hundreds of kilometers per second relative to the galactic center, yet this speed does not create a sense of disorder. The scale of the galaxy is so large that the change in a star's position during a human lifetime is negligible. The calmness perceived from Earth arises from the enormous distances and the slow unfolding of these motions across time. A star may take hundreds of millions of years to complete a single orbit around the center of the Milky Way. The gradual nature of this journey explains why the night sky looks the same from one year to the next, even though everything in it is moving. The structure of the Milky Way also contributes to the consistency of stellar motion. The galaxy contains a mix of stars, gas, dust, and dark matter, all of which influence its gravitational field. This field creates a steady environment for stars to travel through. They do not drift randomly. They respond to the overall mass distribution. Regions with more mass exert stronger gravitational influence, shaping the curvature of the star's paths. This balance allows the galaxy to maintain its long-term structure, even as individual stars move independently within it. Even near the galactic center, where conditions become more complex, motion remains smooth on large scales. The presence of a supermassive black hole introduces stronger gravitational effects, causing stars in that region to move more quickly and along more tightly curved paths. These stars can complete their orbits in far less time than those in the outer regions. Despite the increased speed, their motion remains governed by the same principles. Gravity guides their paths with precision, preventing collisions and maintaining the coherence of the central region. Their behavior reflects the underlying stability of gravitational motion, even in an environment where forces are stronger. Interactions between stars occasionally adjust their paths. When two stars pass each other at relatively close distances, their mutual gravity can alter their velocities or change the shape of their orbits. These encounters are gentle due to the immense distances between stars. Collisions are extremely rare. Most interactions simply introduce small shifts that accumulate over long periods without disrupting the overall order of the galaxy. This contributes to the galaxy's stability. Individual motions may change slightly, but the overall pattern remains intact. Gas and dust within the Milky Way also move along paths shaped by gravity. Clouds of gas drift through the galaxy, responding to the same gravitational influences as the stars. They occasionally collide or merge, triggering new episodes of star formation. Their motion provides a reservoir of material that contributes to the evolution of the galaxy. These flows are slow and steady, unfolding over immense timescales. Their behavior demonstrates that motion does not need to be rapid or dramatic to have significant effects. The combined movement of all these components creates the rotation of the Milky Way. The galaxy does not spin like a rigid object. Instead, different regions rotate at different speeds, a pattern known as differential rotation. Inner stars complete their orbits more quickly than those farther out. This rotation reflects the distribution of mass within the galaxy and the conservation of angular momentum from earlier stages of its formation. The smoothness of this rotation contributes to the familiar spiral shape seen in many galaxies. By recognizing how stars and interstellar material move within a galaxy, the calm appearance of the night sky gains new depth. Each point of light participates in a journey that spans vast distances and durations. These motions continue without rush, shaped by predictable forces and unfolding across immense scales. The galaxy remains coherent because gravity guides these movements into stable patterns. The result is a universe where motion and stability coexist, revealing the quiet dynamics that support the structure of the cosmos. Even in the quietest regions of space, where light is faint and temperatures drop to near their lowest possible values, motion never disappears. At the smallest scales of nature, atoms and their components are always in activity. Electrons occupy regions defined by probability rather than fixed paths, and their behavior creates constant fluctuations. The protons and neutrons within atomic nuclei also move due to the forces that bind them together. These motions occur far below the threshold of human perception, yet they form the foundation of many physical processes that shape matter throughout the universe. The vibration of atoms forms one of the most familiar types of microscopic motion. In solids, atoms are arranged in structured patterns, yet they continually vibrate around their positions. The strength of these vibrations depends on temperature. At higher temperatures, atoms move more vigorously, and at lower temperatures, their motion slows. Even so, the motion never ceases completely. The lowest possible temperature, known as absolute zero, represents the point where atomic motion reaches its minimum. However, quantum mechanics shows that atoms retain a small amount of movement even at this limit. This residual motion reflects the inherent nature of particles and the rules that govern them. In gases, motion becomes more apparent. Molecules travel freely through space, moving in straight lines until they collide with other particles or surfaces. These collisions redirect their paths, creating a dynamic environment where motion is continuous. The behavior of gases in interstellar space follows similar principles, although the distances between particles are enormous. Even when there are only a few molecules in a large volume, they move at high speeds, shaped by temperature and occasional interactions. This movement plays an important role in the behavior of interstellar clouds and the formation of stars. Microscopic motion also influences the chemistry of the universe. When atoms and molecules collide, they can exchange energy, form new bonds, or break existing ones. Reactions occur because particles move and meet under the right conditions. In dense regions, such as collapsing clouds or the interiors of planets, these interactions become more frequent. Energy transfers, chemical changes, and the formation of complex structures depend on the continuous movement of particles. Without this underlying motion, the processes that create planets, atmospheres, and even life would not occur. Another aspect of microscopic motion emerges from the quantum behavior of particles. Even in a vacuum, fields fluctuate, creating brief appearances of particle pairs that form and vanish. These fluctuations contribute to the energy of empty space, demonstrating that motion and activity exist even where matter is scarce. The vacuum is not a place of perfect stillness. It contains subtle forms of motion that influence the behavior of particles and fields across the universe. These effects become significant when studying phenomena such as the expansion of space or the behavior of particles near black holes. Temperature provides a useful measure for describing the motion of particles. It represents the average kinetic energy of the atoms or molecules in a system. Higher temperatures correspond to faster motion, while lower temperatures indicate slower movement. In the depths of space, temperatures often fall to extremely low values. Still, particles retain enough motion to shape their environment. For example, in interstellar clouds, the slow drift of molecules contributes to the cooling and condensation of material, setting the stage for new episodes of star formation. The presence of microscopic motion everywhere underscores a key idea. Stillness is not a natural state for matter. Even when motion becomes subtle, it continues to influence the behavior of particles and the structure of matter. The universe operates through an unbroken chain of activity that spans the smallest and largest scales. This activity does not appear chaotic. It follows clear physical principles that guide the behavior of atoms, molecules, and fields. The calm that seems to fill the vastness of space coexists with this quiet but constant motion. By looking closely at the behavior of matter on these tiny scales, it becomes easier to understand why motion cannot be removed from the universe. It is not an added feature, it is a basic expression of the laws of physics. Whether in the vibration of atoms, the drift of molecules, or the fluctuations of quantum fields, motion persists everywhere. These small motions play essential roles in the formation of structures and the flow of energy, helping maintain the continuity of processes across the cosmos. Temperature offers a clear way to understand motion at the smallest scales because it directly reflects how quickly particles move. When a substance is warm, its atoms and molecules shift, vibrate, and collide with greater energy. When it is cold, their movement slows. This relationship between temperature and motion forms the basis for many familiar behaviors of matter. Even so, there is a limit to how much particle motion can decrease. As a material cools, its particles approach a minimum level of activity, but they never come to a complete stop. This is because the laws of quantum mechanics prevent particles from reaching a state of perfect rest. The idea of absolute zero describes the theoretical point at which particles would have the least possible motion. Yet even at this extreme, a small amount of activity remains due to the inherent uncertainty in a particle's position and momentum. This means that no part of the universe, no matter how cold, can achieve perfect stillness. The coldest regions of space, such as dense molecular clouds or the environments surrounding certain cosmic structures, approach this limit but never reach it. Their particles drift gently, vibrating in patterns that reflect both the temperature and the underlying quantum nature of matter. The role of temperature becomes especially clear when observing how it influences the state of matter. In hot regions, such as the interiors of stars, the motion of particles is intense. Atoms collide with enough force to overcome their electrical repulsion, allowing nuclear fusion to occur. This rapid movement supports the generation of energy that shapes a star's behavior. In cooler regions, such as planetary atmospheres, particle motion determines the transfer of heat, the formation of weather patterns, and the behavior of gases and liquids. Temperature acts as a measure of how actively particles interact with one another, linking microscopic motion to large-scale phenomena. In the depths of interstellar space, temperature plays a quieter but equally important role. The low density of particles means collisions occur infrequently, yet the movements that do happen influence the long-term behavior of gas clouds. A slightly warmer cloud may resist collapse because its particles move too quickly for gravity to draw them together efficiently. A slightly cooler cloud may contract more readily, setting the stage for the formation of stars. These subtle differences demonstrate how small variations in microscopic motion can guide major cosmic events over long timescales. Temperature also affects the structure of solid materials. In the crusts of planets, atoms vibrate within their organized patterns, and these vibrations influence how materials expand, contract, or conduct heat. Even when solid matter seems rigid and unmoving, its particles remain in motion. This constant activity helps maintain the material's stability and allows it to respond to changes in its environment. Temperature becomes a bridge between the invisible world of particles and the tangible behavior of matter under different conditions. The relationship between temperature and motion is also central to the idea of thermal radiation. All objects emit radiation based on their temperature. Warmer objects emit radiation with shorter wavelengths and greater intensity, while cooler objects emit longer wavelengths. This process stems from the continuous motion of charged particles within the material. As these particles move, they produce electromagnetic waves that carry energy away. This quiet emission occurs everywhere, from the surfaces of stars to the dust between galaxies. It provides a subtle but persistent means of transferring energy across space. By understanding temperature as a measure of motion rather than a separate property, the behavior of matter throughout the universe becomes easier to interpret. Heat reflects activity, and cold reflects reduced but never absent motion. The impossibility of complete stillness reinforces the idea that motion is fundamental. Whether in the flickering of particles near a star or the faint vibration of atoms in the coldest clouds, movement persists. This continuity supports the processes that shape the universe, connecting the smallest fluctuations to the grandest structures. The calm appearance of space does not contradict this. Instead, it hides the ceaseless motion occurring on scales beyond direct perception. Temperature provides a window into that motion, showing how matter behaves, changes, and evolves across different environments. It confirms that motion exists everywhere, from the hottest cores to the coldest voids, revealing a universe where stillness is never truly reached. The idea that absolute rest does not exist becomes clearer when considering how different physical principles interact across every scale of the universe. Even in places where motion seems absent, the laws of physics guarantee that activity continues. Expansion stretches space, gravity shapes trajectories, particles shift according to quantum rules. Energy flows from one form into another. These processes operate continuously, ensuring that the universe never settles into perfect stillness. What appears calm is supported by movements too subtle, too slow, or too evenly distributed to be detected without careful observation. One reason perfect rest is impossible is that motion can only be described relative to something else. A person in a drifting spacecraft may feel completely still, yet the craft is moving around the sun is moving through the Milky Way, and the Milky Way is drifting through intergalactic space. These motions do not require a surface or a reference point. They follow naturally from gravitational influences and the expansion of space. Without an absolute frame of rest, no object can ever be truly motionless. It can only appear so when compared with nearby surroundings that share the same general movement. Quantum principles add another layer to this idea. According to the uncertainty inherent in quantum systems, a particle cannot have both a perfectly defined position and a perfectly defined momentum. If a particle were completely at rest, its position would be known with such precision that its momentum would become uncertain in a way that violates physical laws. Instead, particles always retain some degree of motion. This is not a limitation of measurement, it is a fundamental characteristic of nature. Even in regions cooled to near absolute zero, atoms continue to vibrate or fluctuate because they cannot occupy a state of perfect stillness. The behavior of matter across all scales reinforces this continuous motion. At the level of stars, energy flows outward from fusion in the core to the surrounding layers, creating convection and movement within the stellar interior. On planetary surfaces, heat drives winds and currents, shaping weather and geology. In interstellar space, gas clouds drift and respond to the faint pull of distant masses. Every one of these processes involves motion. None of them can exist without it. The persistence of these behaviors supports the larger structure of the universe, allowing patterns to form and endure over immense spans of time. Even the vacuum of space contains activity. Quantum fluctuations introduce brief appearances of particle pairs that form and vanish almost instantly. These fluctuations contribute to the energy density of empty space, influencing cosmic expansion and the behavior of fields. They reflect the idea that motion is not limited to regions filled with matter. It is present even when only fields and fundamental forces remain. A universe filled with such underlying activity cannot achieve complete stillness, because the foundation upon which everything rests continues to shift. This persistent motion helps maintain the long-term behavior of cosmic structures. Stars orbit galactic centers. Galaxies drift within clusters. Clusters stretch and shift as the cosmic web evolves. These processes do not depend on continual external input. They follow naturally from the conditions present in the universe and the laws that govern those conditions. Motion persists because nothing removes it, and because energy converts from one form to another without ever disappearing. Recognizing that absolute rest has no place in the physical world changes the way the universe can be understood. Stillness becomes a perception created by limited senses rather than a reflection of reality. At a deeper level, everything participates in a quiet, unbroken continuum of motion. This motion does not diminish the calmness of the night sky. Instead, it explains it. Large-scale motions unfold too slowly to notice. Small-scale motions occur too quickly or too subtly to see. The combination produces a picture of serenity supported by activity at every level. The absence of absolute rest is not a sign of disorder. It reveals the consistency of natural laws. Motion persists because the physical principles that shape the universe do not provide a mechanism for complete stillness. This constancy ensures that structures remain coherent and that processes continue to evolve. The universe does not pause. It progresses steadily, guided by rules that apply everywhere and at all times. Energy conservation provides one of the clearest explanations for why motion endures throughout the universe. This principle states that energy cannot be created or destroyed. It can only change form. Motion itself is a form of energy, and whenever it appears to diminish in one place, it reappears elsewhere as heat, light, or structural change. Because energy remains present, motion never ends. It simply shifts between different expressions. This quiet circulation of energy supports the long-term behavior of cosmic systems, allowing them to evolve without ever coming to rest. A clear example of this appears when a cloud of gas collapses under gravity. As the cloud contracts, the particles fall inward, gaining speed. Their motion transforms gravitational potential energy into kinetic energy and then into heat as collisions occur. The rise in temperature eventually becomes great enough to ignite fusion in the core of a forming star. What looks like the slowing of one kind of motion becomes the strengthening of another. The energy does not vanish. It moves into new processes that shape the star's structure and behavior. This flow continues throughout the star's life, guiding everything from convection to radiation. Energy conservation also influences the motion of planets. A planet orbiting its star maintains its path because nothing removes the energy associated with its motion. In the vacuum of space, no friction slows it down. The energy within its orbit remains stable unless acted upon by an external force. This allows planetary systems to persist for billions of years. Their motions reflect the delicate balance between gravitational attraction and the energy held within their paths. Even minor adjustments that occur over time do not erase the overall pattern. They simply redistribute energy in quiet ways that help maintain stability. At the scale of galaxies, energy conservation becomes even more apparent. Stars orbit the galactic center in paths shaped by the distribution of mass. Their motion continues because the energy of the orbit remains constant. When galaxies interact or merge, gravitational forces redistribute energy throughout the system. Some stars may be flung outward, while others settle into new orbits. Yet the total energy of the system stays the same. The motion does not stop. It transforms. The resulting structure reflects the combined history of earlier movements and interactions. Even on these vast scales, conservation ensures that motion remains a defining feature. Light also illustrates the persistence of energy. A photon travels through space, carrying energy across incredible distances. It does not slow down in a vacuum. It continues on its path until it interacts with matter. When it is absorbed, its energy becomes part of the internal motion of atoms or contributes to heating a material. The energy completes a cycle, moving from radiation into new forms. This process links distant regions of space. It communicates information about the past while sustaining the flow of energy from one part of the universe to another. The behavior of black holes provides another perspective on energy conservation. Matter falling toward a black hole gains kinetic energy as it accelerates. Some of this energy becomes heat and radiation in the surrounding disk before the material crosses the event horizon. Powerful jets can form when magnetic fields guide energy outward from the region near the black hole. These jets carry vast amounts of energy into interstellar or intergalactic space. Even in environments that seem to consume energy, motion persists because conservation channels it into new paths. Energy conservation also shapes the thermal history of the universe. After the early expansion, energy spread out and cooled, creating conditions for atoms and later structures to form. As energy continued to flow from stars into space, it maintained temperature differences that influenced planetary climates, the movement of gas clouds, and the behavior of interstellar materials. These flows remain ongoing. They help sustain the processes that give the universe its present form. Nowhere does energy stop moving. It shifts from one expression to another, maintaining the continuity of motion across time. The principle of conservation shows why the universe cannot reach a state of complete stillness. As long as energy exists, motion exists. It does not need to be renewed. It does not require a special force to continue. The laws of physics guarantee that the energy present at the beginning of the universe remains active today in various forms. This persistent activity supports the structure of the cosmos and ensures that motion remains an unbroken thread connecting the past, present, and future. Light offers one of the simplest and most elegant examples of motion in the universe. A photon travels at a constant speed through the vacuum of space, carrying energy from one location to another. It does not slow down, drift off course, or come to rest. Its behavior follows precise physical laws that apply everywhere. Light moves because its nature requires it to do so. This motion helps shape the universe by transporting energy, revealing distant structures, and contributing to the interactions between matter and radiation. When a star emits light, the photons leave its surface and begin a journey that may last thousands or even millions of years. These photons carry information about the star's temperature, composition, and motion. As they travel, they do not need a medium to support their movement. Unlike sound waves, which require air or another substance to propagate, light moves freely through the vacuum. The absence of friction or resistance allows photons to retain their energy until they encounter matter. This quality makes light essential for understanding the universe, because it brings the properties of distant regions into view. When light interacts with matter, its energy transforms. A photon absorbed by an atom may raise an electron to a higher energy level. A photon striking a surface can contribute to heating it. In each case, the energy of the photon becomes part of the motion of particles. The process does not end the motion, it redirects it. The energy travels from the photon into the behavior of matter. When matter later emits light, the cycle continues. This exchange spreads energy across space, connecting regions that may be separated by vast distances. Light also reveals motion through the shifting of its wavelength. When a source of light moves toward an observer, the wavelength becomes shorter, creating a blue shift. When it moves away, the wavelength becomes longer, creating a red shift. These shifts allow astronomers to measure the motion of stars, galaxies, and other cosmic objects. By observing how light stretches or compresses, it becomes possible to determine whether an object is approaching or receding, and at what speed. This connection between light and motion helps map the structure and evolution of the universe. Another important aspect of light is that it shows how motion can occur without mass. Photons carry momentum even though they have no rest mass. This momentum can exert pressure on objects, pushing them very gently. Over long periods, this radiation pressure can influence the behavior of dust, gas, and even spacecraft. Although the force is small, its effect accumulates, demonstrating that motion driven by light is subtle but real. This behavior illustrates how energy itself contributes to the flow of motion in the universe. Light also participates in the behavior of the expanding universe. As space stretches, the wavelength of light stretching across large distances increases. This phenomenon, known as cosmological redshift, reflects the interaction between light and the geometry of space. A photon traveling through expanding space loses energy in the form of longer wavelength, yet it continues its journey without pause. This behavior provides insight into the large-scale structure of the cosmos and the processes that shaped it over billions of years. The way light responds to expansion helps reveal how distances change across time. The cosmic microwave background offers one of the clearest examples of light tracing the early universe. This faint radiation fills the sky equally in all directions. It is the remnant of a time when the universe was much hotter and denser. As space expanded, the radiation cooled and shifted to longer wavelengths. Yet it still carries detailed information about the conditions that existed shortly after the beginning of the universe. The motion of this radiation, its uniformity, and its slight variations reveal the distribution of matter in the past and the processes that shaped the large-scale structures observed today. By considering the behavior of light, it becomes clear that motion serves as a means of communication throughout the cosmos. Light travels across enormous distances, bringing energy and information from regions far beyond direct reach. It interacts with matter, influences the formation of structures, and responds to the expansion of space. The calm appearance of the night sky depends on this continuous flow of light. Every point of brightness is a record of motion that began long ago. Light moves without interruption, reinforcing the idea that rest is not a defining condition of the universe. Motion persists at every level, from the smallest photon to the grandest cosmic structures. Time becomes meaningful only through motion. Every physical process, from the oscillation of an atom to the orbit of a planet, creates a sequence of events that can be measured, compared, and ordered. Without motion, there would be no way to distinguish one moment from the next, because nothing would change. The passage of time, as experienced in daily life and understood in scientific study, arises from the continuous activity occurring throughout the universe. This link between time and motion does not depend on any single process. It emerges from the fact that physical laws ensure that matter and energy do not remain in a fixed state. Atomic clocks illustrate this relationship clearly. They keep time by measuring the frequency of specific transitions in the electrons of atoms. These transitions represent regular, repeating motions at extremely small scales. The reliability of these motions allows time to be tracked with remarkable precision. Without the continuous activity of electrons within atoms, these clocks would not function. The definition of a second depends on microscopic motion that remains stable and predictable. This reveals that timekeeping itself is rooted in natural processes that unfold without pause. On larger scales, celestial motions have long provided a reference for time. The rotation of Earth creates the cycle of day and night. The orbit of the planet around the Sun defines a year. These motions occur because the Earth retains momentum and gravity guides its path. They do not require constant input of energy. They persist because nothing removes the motion, and because the forces acting on the system remain balanced. The reliability of these motions allowed early civilizations to create calendars and track the passage of seasons. Even now, these cycles remain fundamental to daily life. The connection between time and motion also appears in the behavior of particles. The decay of unstable particles follows specific patterns determined by probabilities. These decays represent another form of motion, where particles transform into others through interactions. Their timing creates measurable intervals that provide insight into the underlying physics. Without continuous processes such as decay, transformation, and interaction, time would not have the markers necessary to exist as a concept. It is the activity within matter that creates the rhythm of time. Motion also affects how time is experienced. According to the theory of relativity, the passage of time depends on the speed of an object and the gravitational field it occupies. A clock moving at high velocity ticks more slowly relative to a stationary one. A clock in a strong gravitational field also runs more slowly than one in a weaker field. These effects do not occur because the clocks malfunction. They arise because time itself is intertwined with motion and gravity. The structure of space-time adjusts based on how objects move and where they are located. This deep connection shows that time cannot be separated from the physical processes that shape the universe. The expansion of space provides another example of time's dependence on motion. As the universe grows, the distances between galaxies increase. This change unfolds gradually, reflecting the passage of time on a cosmic scale. The expansion rate itself becomes a measure of time's flow across the universe. Light traveling through expanding space shifts to longer wavelengths, creating a record of how space has stretched. These changes help reconstruct the history of the cosmos, showing how structures formed and evolved. Time reveals itself through the accumulated effects of motion across billions of years. Even processes too small or too large to observe directly contribute to the experience of time. The movement of heat through matter, the circulation of gases in planetary atmospheres, and the flow of energy in stars all mark the passage of time. These processes unfold continuously, providing evidence that time moves forward as events progress. Their behavior would make no sense in a universe without motion. They rely on the constant transformation of energy and the steady guidance of physical laws. By understanding the connection between time and motion, the continuity of the universe becomes clearer. Time is not a background that exists independently. It is a reflection of the physical processes that never stop. Every vibration, rotation, drift, or transformation contributes to the flow of time. The calm appearance of the universe does not contradict this. Instead, it reflects the steady ways in which motion creates order. Time emerges from these gentle motions, revealing a universe where change, movement, and duration are inseparable. Across the vast stretches of cosmic history, structures evolve through motions so slow and steady that they seem almost unchanged when viewed from the limited perspective of human time. Yet every galaxy, star, and planet participates in a long unfolding of transformation. The processes that shape the universe seldom occur abruptly. They develop over millions, and often billions, of years. By recognizing the quiet pace of these changes, the nature of cosmic evolution becomes clearer. What appears still is in fact slowly adjusting, responding to the laws of physics that direct matter and energy through cycles of formation, growth, and decline. Galaxies provide a striking example of this gradual evolution. A spiral galaxy may appear fixed in shape, but its arms shift slowly as stars move along their orbits. These arms are not rigid structures. They are patterns created by density waves that travel through the galactic disk. Stars enter and exit these regions as they orbit, creating the appearance of persistent spiral arms, even though the individual stars continue on their paths. Over billions of years, interactions with other galaxies may alter a galaxy's shape, shifting it from a spiral to an elliptical form or creating tidal features that gradually disperse. These changes occur gently, shaped by the accumulated influence of gravity across great distances. Star formation also unfolds in long cycles. A cloud of gas may take millions of years to collapse into new stars. Once formed, these stars shine for long periods, often for billions of years, before eventually growing faint or expanding into red giants. Massive stars evolve more quickly, their intense fusion reactions consuming fuel at a faster rate. When such stars end their lives, they may collapse into neutron stars or black holes. The remnants they produce can enrich their surroundings with heavy elements, seeding future waves of star formation. These cycles overlap across time, creating a continuous renewal of matter within galaxies. Planetary systems evolve in similarly gradual ways. Young systems may experience periods of instability as planets and debris interact gravitationally. Over time, these systems settle into stable arrangements. The surfaces of planets change as internal heat, impacts, and atmospheric processes reshape them. These changes are slow, yet they accumulate into landscapes that reflect billions of years of motion and transformation. Even a seemingly quiet world participates in ongoing activity, guided by the same principles that shape stars and galaxies. On the largest scales, the cosmic web evolves through the slow expansion of space and the shifting of mass within it. Filaments stretch, clusters drift, and voids widen. The distribution of matter becomes more refined as gravity pulls material into denser regions. This evolution does not disrupt the overall structure, it enhances it. The web retains its general pattern while adjusting to changes in mass distribution and the flow of energy. The slow pace of this evolution creates a universe that appears orderly, even as it undergoes continuous transformation. The energy output of stars also contributes to long-term changes. As stars radiate energy into space, they influence the temperature and behavior of nearby gas clouds. This can trigger new episodes of star formation or suppress them, depending on the conditions. Over time, these feedback processes shape the development of galaxies. They determine where new stars form, how gas flows, and how structures evolve. The effects unfold gradually, reinforcing the idea that cosmic evolution is a quiet and balanced process. Even dark matter, though invisible, plays a role in the slow evolution of cosmic structures. Its gravitational influence guides the formation of galaxies and clusters. Simulations of cosmic evolution show that dark matter forms a framework upon which visible matter collects. The quiet motions of dark matter halos shape the behavior of galaxies, affecting their rotation, stability, and long-term growth. This influence remains steady across cosmic time, contributing to the continuity of the universe's development. By recognizing these slow but persistent processes, the calm appearance of the universe becomes more understandable. The stars and galaxies may look unchanged to the eye, yet they continuously evolve through motions guided by gravity, energy flow, and the nature of matter. Change does not disturb the stability of the cosmos. It defines it. The universe moves forward through gentle, measured adjustments that unfold across unimaginable spans of time. This quiet evolution reveals a deeper truth. The cosmos remains stable not because it is still, but because its motions follow patterns that endure and adapt, shaping the universe into the structure observed today. Change in the universe rarely happens in sudden leaps. Instead, it unfolds in quiet, continuous steps shaped by the balance of forces acting across immense scales. The distances between objects are so great, and the masses involved so large, that even strong influences operate gently when viewed from a human perspective. This gentle pace helps maintain the stability of cosmic structures. It allows galaxies, stars, and planets to evolve without rapid or disruptive transitions. The slow unfolding of change is one of the reasons the night sky appears calm, even though the universe is always moving. The balance between gravity and motion provides a foundation for this gradual evolution. Gravity pulls matter together, guiding the formation of stars, planets, and galaxies. Motion, in the form of angular momentum or the expansion of space, prevents collapse and shapes the arrangement of structures. Neither influence overwhelms the other on large scales. Instead, they interact in ways that encourage long-term stability. A galaxy does not collapse inward because the motion of its stars provides balance. A cloud of gas does not disperse completely because gravity gradually draws it inward. These interactions unfold slowly, creating predictable patterns of growth and transformation. Energy also contributes to the gentle nature of cosmic change. The energy produced inside stars moves outward through layers of gas, providing heat and light that influence nearby regions. This flow occurs steadily, supporting the long-term evolution of planetary systems and interstellar material. Energy spreads through radiation, convection, and conduction, guiding the processes that shape surfaces, atmospheres, and magnetic fields. These changes often take place over millions of years, and the slow transfer of heat ensures that they unfold smoothly rather than abruptly. The structure of space itself plays a role in moderating the pace of change. As the universe expands, distances between clusters of galaxies increase gradually. This expansion does not accelerate the motion of local systems. Instead, it operates on scales far larger than individual galaxies. The slow stretching of space provides a calm backdrop against which smaller-scale processes can develop. This separation of scales helps maintain order. Local structures evolve through gravity, while large-scale behavior reflects the geometry of the universe. Neither domain disrupts the other abruptly. Even when dramatic events occur, their effects stretch across long periods. A supernova releases enormous energy, but the influence of this event spreads gradually through the surrounding region. Shock waves move outward, interacting with gas and dust, compressing some areas and dispersing others. These interactions may eventually lead to the formation of new stars, yet the entire process unfolds slowly. The remnants of the explosion drift through space for millions of years, mixing with interstellar material and contributing to the long-term evolution of the galaxy. The dramatic moment marks only the beginning of a quiet transformation. Interactions between galaxies also reflect this gentle unfolding of change. When two galaxies approach each other, their gravitational fields begin to influence the motion of stars and gas. Tidal forces may stretch their shapes, creating long streams of material. Over time, the galaxies may merge into a new system, but this process is not sudden. It occurs across hundreds of millions of years. The stars within the galaxies continue to follow smooth paths, adjusting gradually to the changing gravitational landscape. Even major structural shifts proceed with a calm, deliberate rhythm that reflects the scale of the systems involved. The slow pace of cosmic evolution shows that the universe manages change in a balanced way. Motion does not disrupt stability, it supports it. Each process, whether driven by gravity, energy flow, or the expansion of space, contributes to a long chain of transformation. None of these processes require sudden intervention or abrupt cycles. Instead, they advance steadily, guided by principles that remain consistent across time and space. By recognizing how gradually these changes occur, the quiet appearance of the universe becomes easier to understand. What seems still is simply evolving too slowly to notice in the span of a human life. The calmness of the night sky reflects the steady nature of cosmic processes. They move forward without haste, shaping structures that endure for billions of years. The result is a universe where order emerges from motion, and where change unfolds through gentle, predictable cycles rather than sudden shifts. The long balance between expansion and gravity plays a central role in shaping the motion of the universe. These two influences operate on different scales and in different ways, yet they coexist without cancelling each other. Expansion increases the distances between clusters of galaxies, guiding the growth of the cosmic web. Gravity draws matter together on smaller scales, forming stars, planets, and galaxies. The balance between these forces helps maintain the structure of the universe across time. It allows motion to persist in calm and predictable ways, shaping both the large-scale arrangement of matter and the behavior of individual systems. Expansion acts on the universe as a whole. It stretches space uniformly, affecting objects separated by great distances. This stretching does not disrupt the integrity of galaxies or clusters. Their internal gravity remains strong enough to hold them together. Instead, expansion influences the separation between these systems. Two clusters that are far apart experience a gradual increase in distance. This increase unfolds slowly, reflecting the scale of cosmic distances rather than any abrupt change in motion. Expansion provides the framework within which large-scale motion occurs, guiding the evolution of the universe without disturbing local structures. Gravity dominates on smaller scales. Within galaxies, it governs the motion of stars, gas, and dust. It shapes the orbits of planets and the formation of disk around young stars. Gravity collects matter into dense regions and supports the processes that lead to star formation. It does not oppose expansion directly. Instead, it operates in regions where mass is concentrated enough to overcome the stretching of space. This division of influence allows both processes to function simultaneously. Expansion guides the separation of large structures, while gravity organizes the motion within them. The interaction between expansion and gravity also helps explain why the universe does not collapse inward or disperse into complete uniformity. If gravity alone acted on matter, everything would eventually fall together. If expansion dominated at all scales, structures would not form. The two processes balance each other naturally. Gravity draws matter into galaxies, clusters, and filaments. Expansion ensures that these structures remain separated on large scales. This balance maintains the diversity of cosmic environments, allowing different processes to unfold across the universe. Observations reveal this balance in many ways. When astronomers measure the light from distant galaxies, they observe a redshift that reflects the expansion of space. At the same time, the detailed structure of those galaxies shows the influence of gravity. Stars orbit their centers. Gas clouds form new generations of stars. Dark matter clusters to create halos that support galactic stability. The coexistence of these signatures shows that both expansion and gravity shape the universe simultaneously. Their combined effects guide the motion of matter across vast distances and deep time. The balance between these forces also influences the future behavior of the universe. As expansion continues, clusters will drift farther apart, yet gravity will continue to shape the systems within clusters. Stars will age, planets will evolve, and galaxies will interact through gentle gravitational effects. Even as the large-scale structure becomes more diffuse, the motions within galaxies and clusters will persist. This layered behavior reflects the natural division between the scales at which expansion and gravity operate. By recognizing how expansion and gravity share influence, the motion of the universe becomes easier to interpret. Expansion provides the broad backdrop. Gravity draws and shapes matter within that backdrop. Neither influence overwhelms the other. Instead, they create a universe where motion is guided by principles that work together. The calm appearance of the cosmos reflects this cooperation. Structures remain stable because gravity holds them together. Distances grow gradually because expansion stretches space. The result is a universe where motion continues without urgency, shaped by forces that maintain balance across all scales. Inside a star, motion takes forms that are hidden from view yet essential to its existence. Although a star appears calm from the outside, its interior is filled with continuous activity. At the core, hydrogen nuclei move rapidly due to the intense temperature and pressure. Their collisions create fusion reactions that convert hydrogen into helium. This process releases energy that supports the star against the inward pull of gravity. The motion of particles within the core is not random. It reflects a balance between the forces that compress the star and the energy produced by fusion. Without these rapid, continuous motions, a star could not remain stable. As energy moves outward from the core, it travels through different layers in different ways. In some regions, energy moves through radiation, where photons scatter repeatedly as they interact with particles. Each scattering represents a small redirection of motion, contributing to a long, slow journey outward. In other regions, energy moves through convection. Hot material rises, cools, and sinks again, creating circulating currents throughout the star's outer layers. These currents resemble vast, slow-moving waves of gas. They help transfer energy to the surface, where it escapes into space as light and heat. This interplay of radiative and convective motion shapes the star's behavior and contributes to the variation seen across different types of stars. Rotation adds another layer of movement to a star's interior. Most stars rotate because the clouds of gas from which they formed carried angular momentum. This rotation influences the distribution of temperature and pressure within the star. It can also shape the behavior of magnetic fields, leading to patterns of activity such as sunspots or flares. These features appear and disappear over time because of the internal motions that govern the star's surface. Despite these changes, the underlying rotation remains, guiding the movement of material within the star and contributing to its long-term evolution. Magnetic activity provides further evidence of continuous internal motion. When charged particles move within a star, they generate magnetic fields. These fields interact with the motion of the gas, creating complex patterns that can store and release energy. This activity drives phenomena that appear on the star's surface, influencing the emission of radiation and the flow of charged particles into space. Although these processes may seem turbulent, they follow consistent physical rules. The motion that drives them occurs gradually and predictably, contributing to the overall stability of the star. As a star ages, its internal motions adjust. When the supply of hydrogen in the core decreases, the balance between gravity and pressure changes. The core contracts, increasing its temperature and altering the rate of fusion. New layers of motion develop as helium begins to fuse or as outer layers expand. These adjustments do not disrupt the star abruptly. They occur across spans of millions of years, reflecting the calm progression of internal processes. The star evolves because its internal motions reshape the balance of forces at work. Even during dramatic phases, such as expansion into a giant, the underlying changes remain guided by steady, continuous motion. The star's influence extends outward through the flow of energy it emits. The radiation that leaves its surface travels across space, affecting the environment around it. It warms nearby planets, shapes atmospheric patterns, and contributes to the motion of gas and dust in the surrounding region. Stellar winds carry charged particles into space, forming streams that interact with magnetic fields and neighboring objects. These flows represent another form of motion driven by the processes within the star. They extend the star's influence far beyond its visible surface, contributing to the evolution of surrounding systems. By examining the motion inside a star, it becomes apparent that stability in the cosmos does not come from stillness. It comes from the continuous balance of forces and energy flows. A star shines because motion fills its interior. The calm appearance it presents arises from the harmony of these processes rather than the absence of activity. Every layer, from the core to the surface, contributes to a steady rhythm of movement that persists throughout the star's life. This motion supports the star's structure, shapes its surroundings, and connects it to the broader patterns of motion observed across the universe. Planetary systems form and endure through motions that unfold gradually and remain stable for immense periods of time. When a young star emerges from a collapsing cloud of gas, the surrounding disk of material inherits the rotation of the original cloud. Within this disk, countless particles orbit the star in smooth paths, shaped by gravity and their inherited momentum. Collisions between these particles allow them to stick together, forming larger bodies that continue to move along curved trajectories. Over long periods, these growing objects become planets, moons, asteroids, and comets. Each one carries the imprint of the disk's rotation, preserving the motion that guided its formation. As planets mature, they settle into orbits that reflect a balance between gravitational attraction and the energy stored in their paths. These orbits remain stable because nothing removes the motion of the planets. Space offers no friction to slow them down, and the gravitational pull of the star provides a consistent inward influence that keeps their motion aligned. The result is a system where each planet follows a predictable route, completing cycles with remarkable regularity. These motions define the structure of the system. Days and seasons arise from rotation and revolution, while long-term stability reflects the enduring nature of orbital motion. Moons add another layer to this ordered complexity. They orbit their parent planets while the planets orbit the star. Their paths represent interactions between local gravity and the broader motion of the system. Tidal forces can influence their behavior, causing small adjustments in their orbits or rotations. These effects unfold slowly, ensuring that the system remains stable despite the small changes taking place. Even when moons migrate slightly or become tidally locked, the underlying motion continues without interruption. The system adapts in quiet, predictable ways. Asteroids and comets also participate in this long-term choreography, Asteroids follow paths influenced by the combined gravity of planets and the star, often settling into belts where their orbits remain stable. Comets travel along elongated trajectories that carry them far from the star before returning. Their motion reflects the balance between the star's pull and their inherited momentum. Although their paths can be influenced by encounters with planets or other bodies, these changes do not dissolve the system. They simply adjust the motion, adding variety while preserving the overall order. Even subtle interactions shape the behavior of planetary systems. When two planets move in resonant orbits, their gravitational pulls reinforce a repeating pattern. These resonances enhance stability rather than disrupt it. They create predictable relationships between orbital periods, allowing motion to support the structure of the system. Over long spans of time, resonances can shift or new ones can form, yet the system remains coherent. This quiet adaptability reflects the resilience of motion guided by gravity. Stars in multi-star systems show similar patterns. When planets orbit multiple stars, their paths are shaped by the combined gravitational influence of all stellar components. Although these systems are more complex, their motions remain orderly. The planets follow routes determined by the balance between the star's gravity and their own momentum. The slow unfolding of these interactions demonstrates that complexity does not undermine stability. It becomes part of a larger pattern of motion that endures across time. The long-term persistence of planetary systems shows how motion becomes a stabilizing force. Planets, moons, asteroids, and comets do not remain fixed. They move continuously along paths shaped by forces that remain consistent. Their motion does not indicate instability. It reveals the balance that allows these systems to exist. The calm behavior of a mature planetary system mirrors the calmness observed in stars and galaxies. In each case, motion creates structure, supports stability, and guides evolution. The quiet rhythm of planetary orbits reflects the same principles that shape the larger universe, revealing motion as a natural and enduring foundation. Cycles and repetition play an essential role in maintaining stability throughout the universe. Many cosmic processes follow patterns that repeat with remarkable consistency, creating a sense of rhythm that supports long-term order. These cycles arise naturally from the interplay of gravity, motion, and energy flow. Although the scales vary from the rotation of a planet to the circulation of gas in a galaxy, the underlying principle remains the same. Motion that repeats in a stable pattern provides a foundation on which larger structures can endure. The presence of these cycles reveals the quiet continuity that defines the behavior of the cosmos. Planetary rotation offers a clear example of repetition as a stabilizing force. A planet spins around its axis at a steady rate inherited from the motion of the cloud that formed it. This rotation creates the cycle of day and night, a pattern that continues without significant change for long periods. The motion does not require ongoing energy input. It persists because no external force removes it. This repeated turning shapes the planet's climate, influences atmospheric circulation, and provides a consistent rhythm against which life can evolve. The calm reliability of rotation reflects the stability of conserved motion. Orbital cycles offer another layer of repetition. A planet moving around its star follows a path that repeats at regular intervals. The length of this cycle depends on the balance between the planet's speed and the star's gravitational pull. These orbits define the passing of seasons and contribute to long-term climate patterns. Their regularity arises from the same principles that shape the rotation of the planet. Nothing disrupts the motion, and the forces involved remain constant. Even when orbits shift slightly due to interactions with other bodies, the changes occur slowly and predictably, preserving the overall pattern. Cycles also appear within stars. The movement of energy from the core to the surface can create oscillations, where the star expands and contracts in repeating patterns. These oscillations help reveal the star's internal structure and temperature distribution. They do not disrupt the star. They emerge from the balance between pressure, temperature, and gravity. Similar cycles appear in the magnetic activity of stars. The rise and fall of magnetic features unfold over long periods, yet the underlying structure remains intact. These patterns show that repetition provides stability even within the dynamic environments of stellar interiors. In galaxies, cycles occur on much larger scales. Waves of star formation move through spiral arms as gas accumulates in certain regions. Stars form, live, and eventually release material back into the interstellar medium. This material contributes to future generations of stars, creating a continuous cycle of transformation. The motion of stars along their orbits supports the persistence of these patterns. As stars pass through spiral arms, their presence helps maintain the density waves that define the galaxy's shape. The galaxy does not remain unchanged, yet the repeated processes within it sustain a recognizable structure across billions of years. Interactions between celestial bodies also lead to repeating behaviors. Binary stars orbit each other in cycles that reflect their mass and distance. Their motion shapes the distribution of energy and material within the system. Planets in resonance with one another follow orbital periods that relate through simple numerical ratios. These resonances create repeating gravitational influences that help stabilize the system. Over time, the resonance patterns can shift or adapt, yet they continue to support the overall order. This adaptability shows that cycles do not need to be rigid to maintain stability. They only need to follow consistent principles. Even processes that unfold across enormous distances participate in cycles. The distribution of gas in the cosmic web follows patterns influenced by gravity and expansion. Gas flows toward dense regions, forms stars, and then returns to the interstellar medium through stellar winds and supernova events. These cycles unfold slowly, yet they persist because the underlying physical laws remain unchanged. Their repetition contributes to the evolution of galaxies, shaping the long-term behavior of matter across the universe. By observing these repeating patterns, it becomes clear that cycles provide a means of preserving structure and coherence. Motion that returns to familiar states supports environments that remain stable even as they change gradually. The calmness of the universe arises not from stillness, but from the steady rhythm of cycles unfolding across time. These cycles reflect the harmony between forces and motion, revealing how the universe maintains its order through repetition rather than rest. Entropy often appears as a concept associated with disorder, yet in the context of the universe, it provides a gentle direction for the flow of energy rather than a force that disrupts motion. Entropy increases as energy spreads out, moving from concentrated regions to more even distributions. This tendency influences how processes unfold, guiding them towards states that require less energy to maintain. Rather than causing chaos, entropy ensures that energy transitions occur in predictable ways. It helps explain why certain motions slow while others continue, and why the universe evolves with a calm and steady rhythm. In many systems, energy begins in a concentrated form. A newly formed star, for example, contains a dense, hot core where fusion reactions generate enormous amounts of energy. Over time, this energy flows outward, heating the star's outer layers and radiating into space. The outward flow of energy increases entropy, spreading heat more evenly across the surrounding environment. This process does not diminish the motion inside the star, it supports it. The movement of particles in the core, the convection within the outer layers, and the emission of radiation all reflect the natural spread of energy. Entropy guides these processes, ensuring they unfold smoothly. On planetary surfaces, entropy influences climate and geological activity. Heat from a star warms the planet's surface, creating temperature differences that drive winds, ocean currents, and weather patterns. These motions move heat from warmer regions to cooler ones, increasing entropy by distributing energy more evenly. This redistribution does not create instability. It produces long-term patterns that help regulate the environment. The slow flow of energy through a planet's atmosphere and interior reflects the natural progression toward equilibrium, shaped by the laws of thermodynamics. Entropy also plays a role in the behavior of interstellar gas clouds. When such a cloud cools, its particles lose energy, making it more likely to collapse under gravity. As the cloud contracts, gravitational potential energy converts into heat, increasing the entropy within the cloud. This increase supports the processes that lead to star formation. Even when the cloud fragments or changes shape, the flow of energy follows predictable patterns. Entropy does not create disorder on a cosmic scale. It guides the cloud through a smooth transformation, allowing new structures to form. In galaxies, the long-term flow of energy shapes the cycle of star formation and evolution. Stars radiate energy into the interstellar medium, enriching it with heat and new elements. Over time, this material cools, condenses, and forms new stars. Each stage reflects an increase in entropy as energy spreads outward from concentrated regions. This process continues across billions of years, maintaining the gradual evolution of galaxies. The motion of stars, gas, and dust within these systems reflects the balance between gravitational forces and the natural flow of energy guided by entropy. The result is a stable progression rather than a chaotic dispersal. Entropy also helps explain why complete stillness cannot occur. If a system reached perfect uniformity with no energy differences, no motion would take place. Yet the universe contains many forms of energy stored in stars, planets, magnetic fields, and gravitational structures. These energy sources naturally move toward more even distributions, creating motion as they do so. The flow of heat from hot regions to colder ones, the movement of gas in response to pressure differences, and the gradual evolution of structures all arise from this principle. Entropy does not force motion to stop. It ensures that motion continues as energy shifts from one state to another. The expansion of space contributes to the overall increase in entropy by stretching radiation and spreading energy over larger volumes. As light travels through expanding space, its wavelength lengthens, distributing its energy more thinly. This process supports the long-term cooling of the universe, yet it does not eliminate motion. Stars continue to form, galaxies continue to evolve. The gentle increase in entropy guides the universe toward a state where energy becomes more evenly distributed, but the journey toward that state involves continuous activity. By understanding entropy as a measure of energy's natural tendency to spread, it becomes clear that this principle supports the stability and evolution of the cosmos. Entropy does not undermine the orderly behavior of the universe. It provides direction for the motion of matter and energy. The calmness observed in the night sky reflects this guiding influence. Motion persists because energy remains active, and entropy ensures that the flow of energy unfolds in predictable and balanced ways. The universe moves at its own pace, guided by physical laws that contain no urgency. Every process, from the orbit of a planet to the drift of a galaxy cluster, unfolds according to the conditions present and the forces at work. There is no external clock compelling the cosmos to accelerate or slow down. Motion follows natural rhythms that arise from gravity, energy flow, and the expansion of space. Because these influences operate steadily, the universe evolves in a calm and measured way. This lack of haste is not a limitation. It is a defining feature of how large-scale systems maintain stability across immense periods of time. The expansion of space exemplifies this unhurried behavior. The increase in distance between galaxy clusters does not happen abruptly. It occurs gradually, following a rate determined by the properties of space and the energy it contains. From a human perspective, the change is imperceptible. Over hundreds of millions of years, however, the effect becomes clear. Clusters drift apart, and the cosmic web stretches into larger patterns. This slow process does not disrupt the structure of galaxies or the behavior of stars. It provides a stable backdrop against which smaller-scale motions continue without interference. Stars also reflect this natural pacing. Their internal processes evolve steadily. Fusion in the core proceeds at a rate determined by temperature, pressure, and the availability of fuel. These conditions change gradually as the star ages. A star does not suddenly transition from one phase to another. It adjusts over millions or billions of years. The slow increase in brightness, the expansion into a giant, and the eventual cooling into a remnant all occur through a continuous balance of forces. The measured pace of these changes supports the star's stability, allowing it to shine consistently across long epochs. Planetary systems follow similar rhythms. A planet's orbit does not shift dramatically from one moment to the next. Gravitational interactions with other bodies may alter its path, but these changes accumulate slowly. Tidal effects may cause a moon to drift outward or a planet's rotation to change slightly, yet the underlying pattern remains. These gradual modifications preserve the stability of the system, allowing it to endure across time without sudden disruptions. Even when a system experiences a period of instability, the adjustments unfold through a series of small steps rather than abrupt leaps. The behavior of galaxies further illustrates the absence of urgency. Stars orbit their centers in cycles that take hundreds of millions of years to complete. Density waves move through spiral arms at speeds that shape the distribution of stars and gas without rushing the process. Interactions between galaxies, including mergers, proceed across vast stretches of time. Two galaxies may begin to influence each other long before they finally merge. The blending of their structures occurs as a slow, graceful transformation rather than a sudden collision. The result is a new system shaped by motions that unfold with patience. Even dramatic events, such as supernova explosions, fit into this broader pattern of calm evolution. While the explosion itself is rapid, the consequences extend across long periods. The material ejected by the star drifts outward, cooling and mixing with the surrounding medium. Shock waves compress nearby gas clouds, potentially triggering new star formation. The entire sequence becomes part of a cycle that may span millions of years. The sudden release of energy is absorbed into the quiet rhythms of cosmic evolution, guiding future structures without disrupting the overall stability of the universe. This lack of rush in cosmic processes highlights the nature of the physical laws that govern motion. They do not impose deadlines. They do not require the universe to reach a particular state within a fixed period. They allow structures to develop according to the interactions between matter, energy, and space. The calm progression of these processes reveals how the cosmos maintains order. By unfolding slowly, systems have time to adjust and respond to changes without losing coherence. The night sky appears serene because the rhythms that shape it move on timescales far beyond human experience. Stars drift so slowly that their positions seem fixed. Galaxies evolve at a pace that requires deep time to appreciate. The expansion of space stretches across billions of years. This quiet unfolding of motion is not accidental. It reflects the natural manner in which the universe operates. The absence of urgency allows structures to form, persist, and transform gracefully, creating the calm order that defines the cosmos. As the universe ages, its structures grow quieter, yet motion never ceases. Stars exhaust their fuel and begin to fade. Galaxies form fewer new stars as their reservoirs of gas become depleted. Even so, the universe remains active. The large-scale expansion continues. Galaxies drift through the cosmic web, and remnants of ancient stars move along paths shaped by gravity. The gradual slowing of some processes does not imply stillness. It signals a shift in the forms that motion takes. The cosmos enters quieter eras not because motion disappears, but because the nature of motion changes as energy spreads and structures evolve. When a star reaches the end of its life, its internal processes alter. A star similar to the Sun expands into a giant and eventually sheds its outer layers. The remaining core cools into a white dwarf, a dense and faint remnant. Although the star no longer produces energy through fusion, its atoms continue to move. Electrons within the dense material respond to pressure and temperature. Over billions of years, the remnant emits heat into space, gradually cooling. This cooling represents a slow transformation of internal motion, not an end to activity. Even in its quietest state, the remnant remains governed by the same physical principles that shaped its earlier life. More massive stars leave behind neutron stars or black holes. Neutron stars rotate rapidly, often many times per second, because the angular momentum of the original star becomes concentrated in a much smaller object. Their rotation may slow over time, but it continues through interactions with magnetic fields and surrounding matter. Black holes also participate in motion. They may orbit within galaxies, interact with nearby stars, or influence surrounding gas through their gravitational pull. Although they emit no light from within their event horizons, the environment around them remains dynamic. Gas falling toward a black hole forms disks that rotate rapidly, producing radiation through friction and magnetic activity. The quietness of these remnants is only apparent from a distance. Their motion persists in concentrated and powerful forms. Galaxies also evolve into quieter states. In earlier eras of the universe, galaxies formed stars rapidly as gas clouds collapsed under gravity. Over time, much of this gas became locked within stars or dispersed through interactions and winds. As the supply of cold gas decreases, star formation slows. The galaxy becomes filled with older stars, and its appearance changes. Yet the stars continue their orbits, and the galaxy maintains its rotation. Even when a galaxy enters a phase of relative calm, its internal motion remains. The arrangement of stars shifts slowly as they move along their paths, responding to gravitational influences that evolve over time. Clusters of galaxies also reflect this quiet evolution. As galaxies within a cluster drift and interact, their positions and velocities adjust. Dark matter halos merge gradually, shaping the cluster's gravitational landscape. Over billions of years, the cluster settles into a more stable configuration, yet the motion of its components persists. The galaxies continue to orbit the cluster's center of mass. Their paths remain smooth, influenced by the combined gravity of visible matter and dark matter. The cluster expands slowly as the cosmic web stretches, yet it retains its overall structure. On the largest scales, the expanding universe grows increasingly diffuse. As galaxy clusters drift apart, regions of space become more isolated. The cosmic microwave background cools further, and radiation spreads more thinly across space. Despite this, motion continues. Galaxies orbit within their clusters. Stars evolve within galaxies. Remnants radiate heat or influence surrounding matter. The expansion itself remains a form of motion that shapes the future of the cosmos. The early universe displayed rapid and energetic processes as structures formed and evolved. Over time, these processes settled into steady patterns. The transition from energetic youth to quiet maturity mirrors the life cycle of individual stars. The universe becomes less dramatic in appearance, yet it remains active on scales that unfold slowly. The calmness observed in later eras reflects the gradual distribution of energy and the persistence of motion within enduring structures. By recognizing the nature of this quiet activity, the future of the universe appears not as a fading into stillness but as a continuation of motion in more subtle forms. The cosmos becomes quieter but never silent. Its stability in later eras arises from the same principles that shaped it in earlier times. Motion, guided by gravity and energy conservation, continues to define the behavior of matter. The unfolding quietness reveals an enduring truth. The universe remains active even when its brightest moments have passed, carrying forward the motions that began in its earliest stages. The far future of the universe is often described as a place of growing quiet, where familiar structures become more diffuse and energy becomes more evenly spread. Yet even in this distant era, motion continues. Expansion does not come to a halt. Stars and galaxies do not freeze in place. Instead, the forms of motion shift as conditions change, creating a cosmos in which activity persists, even when many of the processes known today become rare. The subtle motions of this future reflect the same physical laws that govern the present, revealing a continuity that extends across all of cosmic time. As expansion carries galaxy clusters farther apart, interactions between distant structures become less common. A galaxy that once belonged to a rich cluster may eventually find itself isolated. The stars within it will still move along their orbits, but the influence of neighboring galaxies will diminish. The galaxy's rotation will continue, guided by the distribution of mass and the presence of dark matter. Even without frequent encounters or new waves of star formation, the internal motions of the galaxy remain. They do not depend on external activity. They follow from momentum accumulated long ago. Individual stars will also carry motion far into the future. As new star formation slows, the stars that remain will evolve through familiar stages. Many will become white dwarfs, cooling gradually as they radiate heat into surrounding space. The motion of particles within these remnants will continue, though at lower temperatures. Their faint glow will last for billions or trillions of years, gradually diminishing but never ceasing abruptly. Some stars will become neutron stars or black holes. The rotations of these compact objects persist, though they may slow as energy radiates outward through magnetic or gravitational processes. Even when light becomes scarce, these remnants continue to move and influence their surroundings. On larger scales, the expansion of space shapes the future behavior of motion. As distances grow, light traveling between far separated regions stretches to longer wavelengths, eventually becoming too diffuse to detect. Yet the photons continue their journey. The expansion does not stop them. It simply alters their energy. This quiet stretching of light provides evidence that motion persists even when it becomes subtle. The movement of radiation across an expanding universe remains a constant, connecting distant regions through the passage of time. Gravitational interactions continue to operate in the far future as well. Even when galaxies drift apart, the systems they contain retain their internal gravitational relationships. Stars orbit remnants at galactic centers. Clusters of stars respond to local gravitational gradients. Smaller structures remain coherent long after larger ones become isolated. Gravity does not weaken with the passage of time. It continues to guide motion wherever matter remains. The long-term behavior of these systems may become increasingly gentle, but the underlying forces persist. Some predictions suggest that over extremely long periods, stars and remnants may drift out of their galaxies, influenced by slow gravitational interactions or disturbances accumulated across vast stretches of time. Even in this diffuse future, motion remains consistent. Objects continue to travel through space at steady speeds, carrying with them the history of earlier eras. The universe becomes more open and quiet, yet it does not fall into a state of perfect stillness. Motion endures because nothing removes it. Conservation laws ensure that once energy and momentum exist, they persist unless transformed by specific processes. The presence of dark energy adds another layer to this picture. If its influence continues, the expansion of the universe will accelerate, creating increasing separation between distant regions. This acceleration shapes the future trajectory of galaxies and clusters. Although the large-scale structure becomes more diffuse, local systems remain bound. Their motions reflect a balance between internal gravity and the expansion of space beyond their boundaries. The accelerating expansion contributes to the universe's quietness, not by halting motion, but by widening the distances over which motion can be observed. In this future, the universe becomes a place where motion expresses itself through delicate and persistent behaviors. Stars cool slowly, remnants rotate steadily, light stretches into faint signals. Galaxies drift gently apart. These motions unfold across timescales that stretch far beyond human experience. They reflect the natural outcomes of physical laws acting over immense periods. By contemplating this distant future, it becomes clear that motion is not a temporary feature of the universe. It remains present in every era, taking forms that adapt to changing conditions. The quietness of the far future does not represent a fading into stillness. It reveals a more subtle form of activity, shaped by the gradual transformation of energy and the persistent influence of gravity. The universe continues to move, even when its brightest structures have grown dim, carrying forward the legacy of motion that began in its earliest moments. Human perception plays a large role in shaping the impression that the universe is still. The night sky appears motionless because the motions taking place are either too slow, too distant, or too subtle for the senses to detect. Human lifetimes span only a tiny fraction of the time required for stars or galaxies to shift noticeably in the sky. The immense scales involved compress motion into patterns that appear fixed from one generation to the next. This creates the illusion that stability arises from stillness, even though the structures observed are in continuous motion. The limits of perception become clear when considering the motion of stars. Many stars travel at hundreds of kilometers per second relative to the Sun, yet the change in their positions is so gradual that centuries may pass before the shift becomes measurable. The constellations familiar today will eventually distort, but only over tens of thousands of years. The speed of these stars is real, but distance dilutes the appearance of motion. What looks like permanence reflects the smallness of a human viewpoint, rather than the absence of cosmic activity. Galaxies provide an even clearer example. The Andromeda Galaxy moves toward the Milky Way at a significant speed, yet its size and distance make the motion imperceptible. From Earth, it appears as a faint, stable smudge of light. Only through precise measurements does its motion become known. Even the rotation of the Milky Way, which carries the Sun around the galactic center, creates no sensation of movement. The journey takes hundreds of millions of years, far beyond the span in which human senses operate. This mismatch between timescales and perception reinforces the illusion that the universe is fixed in place. Another reason for the appearance of stillness lies in the shared motion of systems. Humans move with Earth as it rotates and orbits the Sun. They move with the Sun as it travels through the Milky Way, and with the galaxy as it drifts through intergalactic space. Because all nearby surroundings participate in the same motions, nothing within the immediate environment appears to shift. This situation is similar to riding in a smoothly moving vehicle. The surroundings inside the vehicle seem still because they share the same motion. The absence of relative movement gives the impression of rest. Distance also conceals motion by reducing the visual effect of movement. A small change in the position of a nearby object may be noticeable, while the same change in a distant object becomes invisible. Stars are so far away that even rapid motion results in minute changes in their apparent positions. These changes require precise instruments to detect. Before the development of such tools, humans naturally assumed that the sky was fixed. The advancement of astronomy has revealed that motion exists everywhere, even when the eye cannot perceive it. The nature of light contributes to the perception of stillness as well. Light from distant stars often travels for hundreds or thousands of years before reaching Earth. The image seen in the sky represents how the star appeared when the light began its journey. Any motion that occurred after that moment has not yet reached Earth. This delay ensures that changes in distant regions unfold slowly from the human viewpoint. The universe appears calm not because it is static, but because the signals that reveal its motion arrive gradually. Cultural expectations further reinforce the illusion of stillness. Because constellations endure across generations, they become symbols of permanence. Stories and traditions link them to fixed patterns, strengthening the impression that the sky is unchanging. Yet the underlying motions continue. The stars drift, the galaxies rotate and migrate. The universe expands. None of these processes stop to accommodate perception. By recognizing the limits of human perception, the calmness of the night sky gains new meaning. What appears still is simply moving at scales beyond immediate experience. The universe does not slow to match human expectations. Its motions unfold across distances and durations that dwarf the human lifespan. The apparent stillness reflects the vastness of the cosmos rather than its behavior. Once this perspective is understood, the quiet patterns seen in the sky can be appreciated as expressions of motion that continue steadily, shaping the universe in ways that transcend ordinary perception. The universe remains coherent not because its structures rest, but because their motions unfold in steady and predictable ways. Every star, planet, galaxy, and particle participates in patterns shaped by gravity, energy flow, and the expansion of space. These patterns persist across immense periods of time, creating the calm order visible in the night sky. What seems like stillness is the result of motion balanced so precisely that it becomes steady. Stability emerges from movement, not from its absence. The cosmos stays in motion because nothing in its nature encourages rest. Its behavior reflects laws that preserve energy, maintain momentum, and guide matter into structures that endure while continuing to move. The smallest scales reveal motion in constant activity. Atoms vibrate and exchange energy. Particles interact through forces that never stop operating. These motions support the behavior of matter and shape the conditions that allow larger structures to form. Without these microscopic movements, the stability of solids, liquids, and gases would collapse. The energy within these systems flows steadily, ensuring that matter responds to changes without sudden or chaotic shifts. This quiet activity contributes to the overall rhythm that defines the universe. On larger scales, stars shine because motion fills their interiors. Particles in the core move rapidly, fusion releases energy, and convection circulates material. These processes maintain a delicate equilibrium that persists throughout a star's life. When a star evolves, its internal motions adjust, continuing to reflect the balance between gravity and pressure. Nothing in a star stands still. Its light is a direct expression of motion carried outward across space, linking the star to its surroundings and contributing to the broader flow of energy throughout the universe. Galaxies reveal motion on an even grander scale. Stars orbit their centers, gas circulates within spiral arms, and dark matter shapes their gravitational fields. These motions define the structure and appearance of galaxies. Even as galaxies evolve, merge, or drift apart through the expanding universe, the underlying motion remains guided by stable principles. Motion does not disrupt galaxies, it maintains them. Their shapes, cycles, and long-term evolution arise from the interaction between gravity and the momentum carried by billions of stars. The largest structures in the universe move as well. Filaments stretch, voids expand, and clusters drift along the cosmic web. The expansion of space gradually increases the distances between these structures, yet their internal motions persist. Expansion provides the backdrop against which gravity operates, shaping matter on smaller scales. The relationship between these influences ensures that motion remains smooth and predictable across all levels of the cosmos. The quiet continuity of motion reveals something essential about the universe. It is not a place where activity arises temporarily before fading. It is a place where motion defines the existence and behavior of everything within it. The appearance of calm does not hide stillness. It reflects harmony. Every motion, whether fast or slow, contributes to the structure and stability of the universe. Motion supports stars, shapes galaxies, guides planets, and sustains the flow of energy across space and time. It connects the smallest particles to the largest structures, revealing a universe unified by activity rather than rest. By understanding motion as a fundamental property, the calmness of the cosmos becomes easier to appreciate. The night sky appears serene because the motions that shape it unfold smoothly across vast distances and immense spans of time. The universe does not rush. It continues steadily, guided by laws that maintain order through gentle and persistent activity. The calm that fills the sky is the harmony of countless motions working together. We, from Sleepy Stories, wish you a good night.